Hello everyone. My name is Advait Gupta and I am the CEO of Paanduv Applications. Very good evening to all of those who are in the evening time zone, and good morning to our viewers from Europe and other parts of the world. Uh, Today we have a webinar on laser 3D printing, especially focusing on the multi-scale modeling of metal 3D printing processes. We have over 1,000 registrations this time in our webinar, and we are very excited to show all the work that our R&D team has put together. And let's get started and let's dive right into it. As far as the flow of this webinar goes, we will be mainly focusing on 4 aspects of 3D printing, which is part scale modeling, macro scale modeling, mesoscale modeling, and microscale modeling. While we will be focusing a lot more on macro scale, mesoscale, and microscale modeling, we will only touch upon a little bit on part scale modeling, simply because we are still working on that aspect, and in one of our future webinars as well, we will try to capture more on the work that we have done on part scale modeling. Before getting started with all the technical details, different case studies, and the current state of 3D printing, especially the metal 3D printing, I would like to whet your appetite with some of the videos that we have generated using CFD simulations, and hopefully many of you will relate to these videos. So we'll start with the laser powder bed fusion, or the more commonly known as LPBF process of 3D printing for 3 different alloys. Next, I will show you a video of direct energy deposition, a wire-fed direct energy deposition. So far, we have been in the macro scale regime. Now what I will, okay, actually the particle spreading using discrete element method is also in the macro scale regime, at least from the numerical point of view. Okay. And now we will switch to smaller scales. Now we are getting into the mesoscale modeling, which is 1/10 or 1/100th of a millimeter. And what we see on the screen is the grain size distribution, orientation, the growth of the grain boundaries as the laser moves over the substrate. We go down to further small scales. Now we are at the micro scale, where we will showcase interdendritic segregation, formation of a dendrite from a nucleus, and then propagation towards the top of the melt pool. The whole point behind showing these videos was to bring your attention to the sheer amount of complexity, the amount of coupled multi-scale physics that is going on between in all of these processes actually. So when we are in the macro scale regime, we have n-phase interface tracking, we have phase change, thermodynamics, surface tension, laser, and particle tracking. When we move on to mesoscale, we are interested in grain growth, orientation, and distribution. When I'm interested in microscale, it's about dendrites, nucleation, propagation, and segregation. Okay. A quick introduction about 3D printing. This is a well-known industry at this point. It's not a really industry which is just starting. I would like to show you some components of aircraft gas turbine that was 3D printed by GE Aviation. I think this was done in 2019 or 2020. This is just to focus that aerospace and defense sector has adopted 3D printing more than the other sectors, and they have actually started making parts that could be potentially used for some sensitive areas of applications such as aerospace and defense. 3D printing is also known as additive manufacturing, and some of the benefits of 3D printing over conventional manufacturing is that it provides design freedom, it has quick lead times, cost-effective process, ease of customization, and simplified workflow. As reported in one of the surveys, as of 2017, there was a $7.3 billion market involved in 3D printing, and 90% of the companies that use 3D printing considered this as a competitive advantage over their competitors. But none of this mitigate the use of conventional manufacturing, because 3D printing cost, while it stays kind of constant as you increase the number of manufacturing units, the conventional manufacturing cost drops significantly if you want to produce higher and higher number of units, right? So there is a sweet point where if you want to make complex parts, fewer parts, then additive manufacturing is a good place to be. If you want to make a very large number of parts and relatively simpler parts, then conventional manufacturing is still an option to go for. As far as the adoption of market goes, like I mentioned earlier, aerospace and defense have been the first and the fastest to adopt 3D printing processes, followed by consumer electronics, medical devices, pharmaceuticals, oil and gas. Chemical industry has limited adoption as of yet, but I hope to see this changing over the next few years. There are primarily two types of additive manufacturing or 3D printing processes that we deal with. One is polymer based, another one is metal based. But in this webinar, we will be mostly focusing on metal based additive manufacturing. These processes are quite complex, involves a lot of laser motion, a lot of thermodynamics and intercoupled physics. So we want to capture these complicated processes and see where the modeling can take us in terms of 3D printing industry. Okay. So why would anybody want to do modeling of 3D printing processes, or what are some of the areas that can potentially be improved in 3D printing processes with or without the use of modeling? Starting with the improved economics due to early defect prediction. I believe this is the largest factor why people want to use modeling. They want to predict if there will be a defect in the part while the part is under 3D printing. Okay. Of course, once the part is made, then you can do a lot of testing, but then that causes loss of money and time. You want to improve the yield, you want to improve more and more parts, you want to improve cycle time, which means the overall process from all the way from starting your 3D printing process to the completion of the process. You want to reduce the times for that. You want to reduce the amount of waste that is generated due to the 3D printing processes. And lastly, process knowledge and innovation, especially on the front of different alloys, their strength, and how best you can use a combination of materials and metals to suit to our application areas. Okay. Moving on to the macro scale modeling, which basically keeps us in the millimeter range. We'll start off with the laser powder bed fusion, or LPBF process. Just a quick refresher on what this LPBF process is. It's a straightforward process where you have a powder bed, a spreader that spreads powder on top of a bed, and the laser scans over the powder particles, melts the particles, and forms a coherent solidified structure. Okay. So if you especially focus on the right image here, you can see the powder bed, okay, and then you can see the solidified material under the laser. Then there's a melt pool, which is just created when the laser hits the powder particles. Okay. In terms of physics, it's a very complicated coupled physics. During LPBF processes involve solid mechanics, solid state transformation, thermal fluid dynamics, and particle dynamics. Especially around the melt pool area, you will see a lot of activity going on. For example, you will see that there is some laser reflections going on when the laser beam hits the melt pool. There is a thermal fluid convection. There are gas pores. Okay, some of the solidification is happening just behind the melt pool. Metal vapor is formed, which is probably ejected out of the system. Some particle entrainment may happen due to gas expansion. Okay, surface deformations, cracking phenomena, second phase precipitation, a lot of things basically are going on simultaneously here. There might be some Marangoni effects going on due to temperature dependent surface tension as well. So there's a reason why this melt pool is not symmetric, because in the hotter parts of the melt pool, the surface tension is lower, and in the colder or the solidified parts of the melt pool, or the under solidification parts of the melt pool, surface tension is higher. So your fluid tends to circulate around and moves and wants to move over to the colder parts of the domain due to higher surface tension there, and that gives the result to some of the characteristic melt pools that we see in the 3D printing, or especially the LPBF processes. Okay. Now, before going deep into LPBF processes, it is a standard practice for any numerical modeling to first look into the validation. I mean, of course, you can use OpenFOAM or any other software to generate some numerical results, but it is important to make sure that those OpenFOAM results actually validate the experimental data. So what we did, we picked up some experimental data for AI-SI 304 stainless steel, and compared the depth and width of our melt pool with the depth and width of the melt pool reported in the experimental observations. Okay, so for example, here we have the experimental image on the left hand side and the real image or the numerical image on the right hand side, and you can see that the images are quite similar here. I want to highlight one more thing, that this is not two-phase system. These are not two-phase problems that we are solving. It's a three-phase problem. The first phase is of course the solid, the second phase is liquid, and the third phase is the inert argon gas, which is typically the case in the real 3D printing processes. Okay, so for this particular case, the laser power is 1250 watts, and the speed of welding is 750 millimeters per minute. Okay, if you look at different speeds of welding or different laser powers, we have a case with 1000 watts of power and a welding speed of 1000 millimeters per minute. And then we have another case where the power is 1250 watts and the welding speed is also 1250 millimeter per minute. Now, if you put together all this data onto a chart and try to validate the depth of penetration against experimental data and another commercial software, we see that OpenFOAM results are excellent. They are very close to the experimental data. For example, in case 2, the depth of penetration as reported in the experiment is 1.48 millimeter, and what we are getting in OpenFOAM is 1.49 millimeter, and same goes for the other cases as well. Now, as we look at the weld width as well, again the OpenFOAM data is doing exceptionally well in comparison to the experimental data. And if you were to report all the error percentages for this validation study, you'll find that depth of penetration ranges from 0.5% to under 4%, and weld width ranges from almost negligible to around 1% error as compared to the experimental data. So this gives us a peace of mind before proceeding with any LPBF simulations, and makes us feel more confident before deploying numerical modeling to more complicated processes, let's say. Okay, so we did an internal case study at Paanduv Applications. What we did a comparison of melting and solidification behavior of different alloys during LPBF, and we made some observations as to what CFD actually reports about these processes. Yeah. So the three different alloys that we have used in the case study is SS316L, stainless steel based. Then we have the traditional Inconel 718, and the last one is titanium based, which is TI6AL4V or TI64. Okay. The main properties where these three alloys differ are basically the thermophysical properties. For example, their molecular weights are different, their melting temperatures are different, heat of fusion, viscosity, thermal diffusivity, density, surface tension, their absorption and emission coefficients when the laser is hit at them, at these metals, and the thermal expansion coefficients, they are all different from each other, and the combination of these variations leads in different outcome when a laser is run over these metals. Moving on to the laser properties, we are using a laser of 280 watts with a distribution of Gaussian type. We have other possibilities for distribution as well in OpenFOAM, but we went with the most realistic one, which is a Gaussian type. The focal radius of the laser is 0.15 millimeters. So you can see we are fairly in the macro scale regime. And then we have turned on the Fresnel reflections and scattering for this case study, but there is an option to activate these options in OpenFOAM, and that will give slightly different depth of penetration in the melt pools. Okay. As far as the powder bed goes, the particle size of powder bed is between 60 to 80 micrometers. The powders are spherical and they have been distributed in a Gaussian manner using lights, which is a DEM based molecular dynamics solver, and it's an open source code provided by Sandia National Lab. The number of layers that the spreader has created is 2 layers. Okay, so there are approximately 2 layers of particles stacked on top of each other. Lastly, the scanning strategy or the process. So the number of tracks that the laser is going to create is equal to 4. The hatch spacing, which is the distance between two tracks. Okay, the vertical distance between two tracks is 0.4 millimeters. The scan speed is 1000 millimeters per second, quite high. And the scan strategy is stripes. So stripes scan strategy is the top left one in the image shown on the right. And the number of phases involved are 3: solid, liquid, and the inert argon gas. Yeah. I will play the video that I played in the beginning of the presentation one more time, and this time I request you to please focus on the difference in temperature profiles as the laser moves back and forth to create 4 different tracks. On the left one we have SS316L, in the center we have Inconel, and the right one we have TI64. You can see that SS316L seems to be more dynamic, seems to be hotter than the Inconel and TI64 alloys. Now, if we wait for these melt pools to solidify, at least partially solidify, we give it some time, then this is what we get. And these are not experimental images. These are the ray traced images that have come out of OpenFOAM. What we see in SS316L clearly is that the tracks are more overlapping. In fact, on the bottom right corner of SS316L, the tracks have completely overlapped and they have formed one big chunk of solidified metal. In the case of TI64 or TI64, the tracks have partially overlapped, but they are clearly visible in a distinct manner. And when it comes to Inconel, the tracks have barely overlapped, and they are very far from each other. If you were to cut the slices through each of those tracks, each of the 4 tracks, and also cut a slice perpendicular to all the 4 tracks, then and if I play this video, then you will see the motion of laser as it melts the powder particles on top, and the formation of melt pools under the powder particles and on top of the powder particles as well. And this is for Inconel. Second track, third track, and then finally the fourth track. At the end of the fourth track, laser is turned off and the metal is allowed to solidify from there. So you can see that the melt pool starts decreasing in size and shape once the laser is turned off. And this is the final image that we have collected. Not a final image. This is slightly after we have turned off the laser. Okay, so you can clearly see the melt pool formation near the top of each of the tracks. Okay. If I were to cut a section that goes through all the 4 tracks, or basically perpendicular to the motion of the laser, then this is what you will get for 3 different materials, for melted SS316L and Inconel and Ti64. Clearly you can see that the stainless steel based alloy is forming more dynamic and larger melt pools. Ti64, I'll play the video one more time, or actually I have a stagnant image of this in the next slide, hopefully. Okay, you can clearly see that that stainless steel based alloy is forming larger melt pool. Ti64 is forming deeper melt pools, and Inconel is actually forming melt pools which are quite shallow, as well as their depth of penetration is not much. Yeah. Again, this is not an experimental photo. This is an image post-processed using or ray traced using OpenFOAM. And what you see here is the different sizes of melt pools in the second track. Okay, you can clearly see SS316L is quite wide and fairly deep. Inconel 718 is not wide, it's not deep, and Ti64 is not wide, but it is penetrating quite deep. Okay, so if we were to summarize all these observations we made from this case study, we can say that as far as the melt pool goes, SS316L forms shallowest but the widest melt pool. Ti64 forms deepest but the narrowest melt pool, and Inconel 718 forms narrow and a shallow melt pool. As far as temperature profiles go, SS316L heats up the most, followed by Ti64 and Inconel. And when we look at the post solidification results, SS316L forms wider and overlapping scan tracks, followed by Ti64 and Inconel 718. As far as the melting goes, SS316L has the most dynamic melt pool with the seemingly stronger Marangoni effects. Okay, moving on to the next process, which is direct energy deposition, or the DED process. There are 2 types of DED processes. One, we inject metal in the form of powder in concentric circles around the laser, and the second one is wire fed, where we basically inject wire and not powder, just a wire in the path of the laser beam. And what happens, the laser melts the powders or the wire, and the molten metal basically sticks to the surface and eventually solidifies, somewhat similar to soldering process. If I play a video for a sample DED simulation, you can see that the wire comes in, the laser shoots at the wire, it melts, and you can see the molten metal is formed, and the bottom substrate is moving in the right direction. Therefore, the molten metal that is formed on top of the substrate is also moving along. I'll play the video one more time in case you missed it. Okay. Uh, we also ran a few sample simulations with 4 phases actually. The reason is sometimes it is important, or it might be important in your specific case, that you want to capture the vapor phase as well. And vapor is like I showed in one of the earlier schematics. Sometimes your solid gets too hot and it turns into vapor directly. Some of your liquid turns into vapor. And then vapor can turn back into liquid, and vapor can also turn back into solid. So there's a lot of phase change possibilities that are going here. So if you think your process requires capturing the vapor phase as well, in addition to the solid phase, liquid phase, and the inert gas phase, then OpenFOAM is a good solution for that, because it is not limited to 2-phase modeling. It is truly n-phase modeling, and it keeps track of all the interfaces that are formed between different phases. So if I play the video on the left, you can see 3 different phases in action. We have solid fraction, liquid fraction, and the vapor fraction. Let me go back. You can see as the laser moves from left to right, all the 3 different phases are formed. And something that we like a lot about OpenFOAM is that it reports the mass transfer rate that is happening between different phases. Yeah. So near the laser area, a lot of liquid is formed. So there's a lot of solid to liquid mass transfer. Liquid to solid mass transfer happens in the solidification zone, which is the bottom right video. And then there is some amount of liquid to vapor and solid to vapor mass transfer also happening. Similarly, if we were to apply the same concept to a stationary laser with 4 different phases simultaneously, then you have inert air, solid metal, and I will play this video one more time because it is running quite fast, and I'll pause this one. So we have inert air, solid metal, liquid metal, and metal vapor. All the 4 phases are tracked simultaneously by OpenFOAM. You can see that there seems to be some expulsion happening due to large amounts of pressure or vapor formation. Seems like some of the liquid will be expelled out of the system. If I were to play the second video, you can see a uniform distribution of particles on a substrate, and how the melt pool is formed. And this is a stationary laser, so you can imagine it will keep expanding the melt pool. I want to highlight the sheer amount of thermophysical coupling that is going on. Your melt pool velocity is dependent on a lot of factors, including temperature, and your temperature is dependent on a lot of factors, including melt pool velocity. And this is where, we also plotted contours for this case, and we could see the Marangoni effect in play. We could clearly see a circulation happening inside the melt pool. Okay, I think you got the point. So if I move on, this is the overall macro scale modeling that OpenFOAM entails. We have laser parameters that involves laser beam diameter, scan speeds, laser power, laser layer thickness, and hatch spacing. There are material properties in play, thermophysical properties for n different phases. We have heat and mass transport going on. All 3 modes of heat transfer, mass transfer, solidification, melting, everything is taken care of. Then we have multiphase physics, where we want to capture multiphase interface. We want to track all the interfaces between all the possible combinations of the phases. There are multiple phase changes involved. And lastly, we have particle size distribution, dynamic mesh motion, and Gaussian heat source involved as well. And all this complete package is included in OpenFOAM, and we used OpenFOAM to exclusively perform this macro scale modeling. Moving on to the smaller scale, which is the mesoscale modeling. A quick introduction as to what we mean by mesoscale modeling. What are we trying to attain here? So solids are composed of a collection of many grains, and each of these grains contains crystals in a certain orientation. Okay. Now, if you add heat and then remove the heat from these solids, this grain structure changes and the boundary of the grain changes. The grains can grow or shrink in size, they can orient in a different direction, and this directly affects the quality of the part in terms of its strength, fatigue, and creep. Okay. So there are, in the images you can see that there are different orientations for the grains, and in some of the upcoming videos I will show you how the orientation and the size of these grains changes if we run a laser over them, which is typically the case in 3D printing processes. Okay. So we use this kinetic Monte Carlo simulator, known to be stochastic parallel particle kinetic simulator, or SPARCS, again thanks to Sandia Labs for all the amazing codes that they keep putting out for free. And it basically captures some of this grain distribution, misorientation, and growth. What our R&D team at Paanduv did, we modified SPARCS so that now it is capable of predicting a grain orientation, Euler angles, and misorientation specifically, and we can visualize them clearly now. Okay. So if you remember the validation or the welding validation from the Microscale modeling, and if we look at the images for case 1 and case 2, what we did, we cut a slice through that welded part, and this is all happening virtually. Okay. We performed a grain distribution analysis for case 2 and case 1. You can clearly see that the grains are distributed quite differently for the two cases. And let me play another video that will give a better understanding of how the grains evolve as the laser moves over them. So in this video, before playing, I want to highlight that the laser will be running twice. Okay, and there will be two layers, so on top of each other, and the three different cubes that you see on top correspond to three different Euler angles. So each grain, like in Euclidean geometry, you can define angle completely by alpha, beta, and gamma. Okay, so each grain can be completely defined by three angles. The orientation of each grain can be defined completely by three angles, and that's why we are seeing three different images for corresponding to different Euler angles. On the bottom we will be seeing the laser. So now if I play the video, okay, so the laser moves once, and you can see how the grain size has changed, how their orientation has changed, and then the laser moves again on top of it, and again the grain size and the distribution completely changes. If I were to go a little further, if I were to use 4 layers instead of 2 layers, this time we will be running laser 2 tracks on layer 1 and 2 tracks on layer 2. Okay, and this time let's see how the grain sizes evolve. Okay, so this is first layer, 2 tracks side by side. Second layer, 2 tracks side by side. Okay, third layer, 2 tracks parallel to each other, and then lastly, fourth layer parallel to each other. And you can see the shear complexity and the amount of grain orientation that has changed because of this heating process. Okay. If we were to look from the top, or if you look at the scan track from the top after one layer, okay, this is how the scan track looks. So initially all the grain sizes were randomly oriented, but once the laser moved through them, based on a lot of material properties, a lot of other properties of the metal itself, you will find different types of grain orientations and grain formations. And if we cut through the welding part, the cross-sectional view, these are the grain orientations at different Euler angles that we'll see. The bottom 4 images indicate that. Okay. Yeah. Something interesting that we found, preferred scanning strategy is typically not parallel for each layer. What they do, they keep changing the scanning strategy on each layer so that your grains do not orient in a specific direction, and that can lead to direction specific cracking in the parts eventually. So I play the videos. This is, you can see on the first layer the laser is parallel to each other, back and forth, but on the second layer it's not back and forth, and it's at an angle of 22.5 degrees. and probably on the third layer it will be at a 45 degrees, and fourth layer it will be parallel again. Idea is to slightly keep it random. Okay. Moving down further to microscale, and now we are getting into micrometer regime. We are going to discuss dendrites. So dendrites are characteristic tree-like structure of crystal growth. Okay, and they specifically grow in the directions which are energetically favorable to the growth of the dendrite. Okay, so what we see on the little GIF on the side is the growth of dendrites. We have 1, 2, 3, 4, 5, 6 arms, and then each arm has secondary dendrite growth on top of it. Okay, so if we were to zoom in at the melt pool boundary, okay, and if we make a schematic out of it, we will most likely see some of the dendrites. So there are three types of dendrites that they have shown here: equifax dendrites, which forms this equally spreading out dendrites with 4 arms. Then they have columnar dendrites, and then lastly they have cellular dendrite. The numbers 100, 100, and 100, it's a preferred orientation, or the natural orientation for the dendritic growth. And the weld pool is on the right hand side, and the welding direction is from left to right in this case. Okay, so these dendrites start forming at the solidification area, and then they kind of get into the melt pool and start solidifying the melted part of the melt pool as well. Okay, there are two important parameters that we want to we typically look at when it comes to dendritic growth or microscale modeling, which is phase field and chemical potential. Okay, phase field is basically like interface tracking for different phases, but in this case what we are tracking is the interface boundary between the dendrite and the liquid. Okay, and chemical potential is a way to understand, or it's a driving force that enables compositional gradient across the grain boundaries. Okay, so for example, you have nickel inside your alloy, and if you want to understand how the composition of the nickel changes as the dendrites are formed, this is something this is a variable that can be used to understand such phenomena. So on the next video I will play a video, on next slide I will play a video, and remember again the validation case, the welding validation case that we had. For case 1, we ran a dendritic study of phase field simulation for case 1, and this is how the dendrites evolve. We provided a nucleation center, and this whole computational domain is inside a small part of the melt pool. We give a nucleation site at the bottom, and the dendrites are forming towards the top, and there is some secondary dendritic formation as well. On the right hand side, we are plotting chemical potential, okay, for the compositional gradient of nickel. Okay, this is used using another open source software called Microscale, and we will be exploring more about this Microscale or microscale modeling in the future. Okay, now if we were to look at mesoscale and microscale modeling, there are 3 aspects to it. Okay, so the process itself, which depends on compositional gradient, thermal history of melting and solidification boundary conditions, depends on the structure of your solid, phase transition temperature, lattice constant, phase fraction, elastic constants, defects, porosity, stress distribution. Okay, and lastly, how does it finally affect the part or the quality of your 3D printed part? It directly affects the strength, toughness, creep, and fatigue of your parts. So this is all to say that if you do macro scale modeling and then move on to mesoscale and microscale modeling, there's a good chance that you will catch the defects earlier, and save on a lot of other complications that may arise later after the part is built. Okay, so going back to our earlier slide, where what we want to attain with all this is, of course, we want to improve our 3D printing processes in terms of defect prediction, yield improvement, cycle time reduction, waste reduction, and we want to enhance our process knowledge and innovation with all this. So therefore, we thought let's wrap all these multi-scale models, all these multi-scale solvers into a single solver where users can seamlessly interact between different scales, and we want to call this product AM Prava, which is a product that will be released. We are still under development, but it will be released sometime later this year. And this AM Prava product basically contains two aspects. Okay, it helps users in intelligent simulation setup with the help of Paanduv repository of original 3D printing simulations and validation. So everything that we have shown in this webinar so far is meticulously done at Paanduv applications. It's all our original content. We have validated some of this material which we could not include in this webinar, and we have more validations that we are running every day. It can capture melt pool dynamics, shape, size, depth of penetration. It will have phase change and chemical potential calculation capabilities, dendritic segregation, grains distribution, DEM for particle spreading. It will have truly multi-phase tracking, and when it comes down to microscale, these simulations are computationally intensive, so GPU parallelization will be included as well. And in order to make it user friendly, we will keep it in the context of traditional laser welding, LPBF, DED, sintering, binder jetting, and FDM. The second, I would say, a more ambitious aspect of this product is going to be performance and convergence prediction, which is not the problem of 3D printing modeling, but it is just something to be careful about when you are into the field of numerical modeling in general, is to be sure about the performance and accuracy, reduce the number of trials and errors, reduce the number of times you tweak your model before you get meaningful results. We are going to use some AI-based, we are developing some AI-based code to improve the accuracy and performance of the results that come out of numerical modeling. Before closing off for the day, a little introduction about Paanduv. We are a company situated in the northern part of India. Primarily, we have a team of CFD software developers and application engineers. We mainly deal with computational fluid dynamics, artificial intelligence, design parameter optimization, innovation, and prototyping. Okay, and we will elaborate a little bit more in terms of what we do, but we do operate in a lot of industries, including 3D printing, water environmental, aerospace, energy, defense, microfluidics, automotive, turbo machinery, and HVAC. Okay, in fact, we have some of the planned future webinars and workshops. These workshops was something unplanned, but it got a lot of traction, and we are doing workshops in drone modeling, battery thermal management, 3D printing, aerospace and defense, water environmental, turbo machinery, and HVAC. It will be very original content, all the way from basic to advanced modeling. And in fact, one of our workshops is coming up on 29th and 30th of January. It's a 2-day workshop. First day we cover the basic and the intermediate, and second whole day we do a case study. Okay, so if you are interested, you can look at the description in the link below, and sign up for the workshop as well. Okay, none of this is possible without the diverse R&D team that we have at Paanduv Applications. We have CFD software developers, research scientists, who are doing solver development, customization, dynamic meshing, aerodynamics, multiphase modeling, reactor modeling, fire modeling, chemical engineering. We have people who are also developing artificial intelligence codes, scientific parallelization, scientific computing, large scale modeling such as water environmental processes, advanced post-processing, mesoscale, and microscale modeling. So I would like to thank our team for all the efforts they are putting together. And lastly, thanks a lot for your time. We had to cut down a lot of slides to keep it under 45 minutes, so we can take any questions that you may have. But if you have any queries, general queries or related to CFD R&D, CFD application, CFD product development trainings, you can always write an email to support@paanduv.com. Okay, and for our latest updates, you can go to our LinkedIn page. That's very active, and that's where you will find all the stuff that is going on in our company. We also have a marketplace called www.paanduv.com, and it's basically an initiative for all the CFD engineers around the world. If you are an engineer, if you can do projects, then you can just sign up and do any of the projects that might be posted by any of the employers. What do? We basically are into CFD software development, migration to OpenFOAM, CFD consulting, CFD training and workshops, CFD experts marketplace, and we also work with tangential technologies such as AI optimization, product design, technology development, and prototyping. So this is it from my end. If you have any questions, feel free to continue posting the questions. I see a lot of questions already. In case some of you missed any part of this presentation, we will send out. Okay, for any additional questions, we'll be very interested to get emails from you guys, and thank you a lot for attending. This really encourages us to put together more such webinars. Please shoot us an email at support@paanduv.com and we will get back to you. Thank you everyone. Have a good day.